In this video, we are going to talk about the properties of real gases. So in the previous video, we talked about what are called ideal gases, but we have to make some postulates about how gases behave for the ideal gases. Namely, that the particles have no size and that they don't interact with each other. But in real gases, those tend not to actually be true, and so we have to account for deviations in what we see with ideal gases in order to come up with the behavior of real gases. So for real gases, as opposed to the ideal gases, we find that the isotherms present aberrations, especially at low temperatures and high pressures. So we can see some isotherms over here, and what we see is at these higher temperature ones, the isotherm looks like the ones that we had for the ideal gases, which is what we saw in the previous video. But as we start getting to these lower temperatures, we start getting these aberrations down here. And this is because, as I said, real gases, the particles do actually have a size and they do actually interact with each other. So let's say we have 1 mole of a gas, and if it's an ideal gas, then if we just get everything onto one side of the ideal gas equation, then it should be equal to 1, where here this V sub m is the molar volume, so it just sort of incorporates both the volume and the number of moles. So we're just getting the ratio of everything here, and if it's ideal, that should be equal to 1. But for a non-ideal gas, we have what's called the compressibility factor, which essentially just means we do this same thing, but then this will not necessarily be equal to 1 like it is for an ideal gas. And so we want to know what the behavior of this Z is. So we can see what's going on with Z here when we look at this figure. So we have on the x-axis our pressure, then over here this is essentially the difference in what the pressure would actually be. So this is what the ideal pressure would be, this is what the actual pressure is. And we see for a bunch of these gases that as we start increasing the pressure, the Z actually goes down, but then as we continue increasing the pressure, it actually goes up. And this kind of makes sense if we think about this conceptually. So when we are at these lower pressures, the particles are going to be interacting, and so they're going to be bending each other's paths, they're going to be colliding with each other in what are actually inelastic collisions, and so what that essentially means is that the pressure will look less than what you would expect it to be. But then as we start really increasing the pressure, so now we're really collapsing the volume down quite a bit, so all the particles are going to start really getting packed in together, and so then the size of the particles is actually going to start making a difference there. So this is because for real gases, as we said, the size of the particles and their electrostatic properties must be taken into account. There are multiple models for doing this. So 2 ways of handling this are what are called the van der Waals model and the Redlich Kwong model, which we'll be talking about here in a little bit. But I wanted to look at some pictures here of what we mean when we say that we are not obeying the postulates of an ideal gas. So because we do have interactions, we deviate from the ideal gas. So in an ideal gas, we assume that we have particle 1 here moving this way, particle 2 here moving that way. When they get close to each other, nothing will actually happen. There will not be any change in their velocity. They will continue in the same direction at the same speed. Whereas for real gases, they are actually going to interact with each other, so they will bend each other's paths. And as I said, if they actually do collide with each other, then there is going to be a less than perfect elastic collision there. Then we can see down here, if we have an ideal gas, so if we then condense it, they could all just sort of overlap in one little spot there. And in fact, that little spot would take up exactly 0 space, and so there would be no space taken up in here. Whereas for a real gas, these particles do actually have a finite size, and so they do take up some space. So if we start condensing them together, they will actually take up some space. And so that's why when we start getting those really high pressures, the size of the particle actually starts taking up some space. That's going to push out even more on the container, and that's why it's going to look like the pressure is even higher than what it actually is. But then, like I said, if we look at a few of these models for handling this, the first one, and there are more than just 2, but I'm just going to be looking at 2 here really quickly. The first one is what's called the van der Waals model. So we see we have this correction term right here for our pressure, and this correction term right here for our volume, where again we're using this V sub m here. This A up here is an experimentally measured value. So this is something that you would actually have to go to a lab, you'd have to make some measurements, and then come up with that number. It's not something you can can get analytically. And so it's an experimentally measured value that has to do with the electrostatic potential of the particles, and B, which is right here, is an experimentally measured value that has to do with the size of the particles. These values can be approximated from the critical point data using these right here, where this T sub C right here is the critical point temperature, and this P sub C here is the critical point pressure. Then we have the Redlich Kwong model, which again just has this term right here for the pressure, and then this term right here for the volume, where again the A is the experimentally measured value that has to do with the electrostatic potential of the particles, and B is an experimentally measured value that has to do with the size of the particles. These values can be approximated from these. So again, this is using the critical point temperature and critical point pressure. And these are just some of the values from both of these. So we have the A and B here for van der Waals. We have the A and B here for the Redlich Kwong. I'm not going to go through each of these in turn, but what we can see if I plot these for the A parameter, we can see that between the van der Waals, which is in blue here, and the Redlich Kwong, which is in the brown here, that they are all roughly the same size. So these are all normalized to the magnitude for the benzene right here. But we can see that in both models, the relative height of each of these is about the same. So the relative magnitude of all of those A parameters are the same. Similarly for B, and in fact, these are even more close, where when I made this, I actually had to go back and look at the data to make sure I didn't just accidentally copy and paste the B data from one into the other one, but these are actually slightly different on here, but they're all extremely close. So again, we can see that the relative magnitude of each of these is the same. So we can also use what's called the Virial model, which uses what's called a Taylor expansion perturbational approach. But essentially it just means that we're taking this ratio right here of all our parameters for the ideal gas law, and we know for an ideal gas that this should be equal to 1. So all these extra terms right here are just correction terms. So if this is not ideal, then it will not just be equal to 1, because we will have these correction terms here that will not be 0. So we have the B, the C, and the D, and so on, where these are the temperature-dependent constants. These so-called virial coefficients essentially take interactions between more and more particles into account. So for instance, the B term here is the pair interaction between particles, where the C term here is the 2 and non-additive 3 body interactions. So these higher order terms just start taking in more and more of these interactions into account. The B term is the largest correction, and so is the one usually discussed. We'll see here in a minute that only using the B term will not give you the exact right answer, but it gives you something quite close. This is because the higher order terms decrease as inverse powers of this volume, and so it quickly becomes negligible for the much higher order terms, since we are doing this volume to some power depending on what term it is. So these are the B coefficients here for some gases, for some different temperatures, and for some what are called boil temperatures for some different gases, which we'll talk about here in just a second. So the virial coefficients vary with temperature. This can be seen in this table up here. So this is for helium, neon, and argon. We see this for different temperatures here, and we see that these do actually change at different temperatures. And there is a temperature at which the virial coefficients go to 0. So remember, if they go to 0, all this stuff right here would go to 0, and it would just be equal to 1, so it would be acting like an ideal gas. So there's a temperature at which the virial coefficients go to 0 that is called the boil temperature. This is known for some gases on the right table up here. So these are the boil temperatures for some of these gases, where the boil temperature is just the temperature at which the gas acts like an ideal gas. So it would act just exactly like an ideal gas at these temperatures. And we can see this by looking at it this way. So we have our Z being equal to this PV over RT. So we want to set this equal to this Taylor expansion right here. But with B equals 0, we see that we just now have 0 over the V right there. So this will be equal to 1. That gives us Z equals 1, which is when the non-ideal gas will act just like an ideal gas. If we compare the van der Waals equation with the Virial equation, we get this right here. And I'm not going to go through how to get from one thing to the other. I do actually have that process in my lecture notes. They're down at the very bottom of it. Lecture notes, as always, are linked to in the description down below, so if you're interested in that, then you can look at that if you want. But we can rewrite this like this, so we have our Z being equal to this 1 over 1 minus this B over V minus this A over RTV. We know at very low pressures, where real gases behave more like ideal gases, the volume gets very large, and so we see that these will both go to 0. So this B over V will go to 0, and so with this A over RT V. So these V's are going to get very large because the pressure is going down, and so these will go to 0. So that would leave us with something like this. So the Z will be equal to 1 here, because we now have this B over infinity, and then minus this A over infinity, where anything divided by infinity is just 0. We can do the Taylor series expansion using this approximation right here. So this 1 over 1 minus x equal to this Taylor expansion right there. So then we get this. So we can collect the like order terms. So that's the stuff that I have in blue right here. We see that we have the B minus A over RT, and this 1 over V sub M was our commonality between the two terms. So we can compare this to the Virial equation. So we get this. So we now have the Z equals this PV over RT. That's equal to this. This is our Virial equation. We can see that because the second order is just the over Vm here, which we have right here, that this in the parentheses must be our B term. So the B minus A over RT. And we know that the Boyle temperature T sub B here is when the second virial coefficient B here is 0. So we can see that 0 equals the B minus A over R. Then we have the T sub B right here. So we can just solve this for the T sub B, and we see that the Boyle temperature can be found by doing this A parameter here divided by the B parameter times R, which tells us that all gases whose behavior can be described using the van der Waals equation of state have a finite, so an actual real Boyle temperature there, and should behave like an ideal gas at that temperature. So for instance, if we look at helium, which has this as its A parameter, this as its B parameter, then we're using this R constant right here. So if we put this into this equation up here, what we find is that this gives us 18.0 Kelvin, but experimentally this is actually 25 Kelvin, so it's not exact. The reason for that is because we dropped those higher order terms. So if we started including more and more of those higher order terms, we would find that this number would start getting closer and closer to this 25K right here. And then let's look at some derivatives of pressure using the van der Waals model. So the van der Waals equation, and now I'm using the regular V, so we'll include the n's here instead of this V sub M, which remember was just the volume divided by the number of moles. So that's why we have to add the N back in here. So we get this, so it's the P plus AN squared over V squared. Then we have the V minus the N times B. That's equal to the nRT. So if we rearrange this to get this in terms of pressure, it looks like this. Next, we want to take the derivative with respect to temperature. So where the second term on the right is not dependent on temperature right here, so this is just going to drop out. And so if we take the derivative of this pressure here with respect to temperature, then this T right here will go away because we're taking the derivative with respect to that T. And so that gives us this right here. Similarly, when we get the derivative with respect to volume, what we end up with is right here. So now this is in terms of volume, so that does not drop out. So that becomes this right here. And then this we have to take with respect to volume. And so with that, we end up with this right here. So we can compare these to what we get for the ideal gas. So the ideal gas derivative with respect to temperature is this right here. Then for the non-ideal gas, or for the real gas, it looks like this right here, which just has this minus N times B factor on it right there. Then if we look at the derivatives with respect to volume, what we see for the ideal gas, we have this right here. Then if we have the non-ideal gas, that turns into this right here. But then we also have this correction factor right here. So that is the derivative with respect to volume for our non-ideal gas. And if we wanted to plot these, it would look something like this. So what we have on this axis right here is our temperature that's increasing left to right. Then on this one right here, we actually have our volume that's increasing from back to front. And so we can see this would be the change in pressure with respect to temperature at a given volume. So in fact, at volume V2 right here, then if we were doing it at volume V1, it would actually look like this over here. And we can see when we're going front and back that we now are looking at the derivatives of pressure with respect to volume at, say, temperature T2, and then over here at temperature T1, then everything in the middle would be things in between there. If you're interested in playing around with these derivatives, I do actually have this Desmos calculator here. You can go on there and play around with those just to look at what those functions look like when you change the different parameters on it. Down here, again, this is just how to derive that thing that I talked about earlier. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.